We're going to be talking about fixing a Dash 17 Bally MPU board. This also applies to Dash 35s or Stern m100 boards. That kind of both apply. The first thing you should note is that we have closed frame auget sockets. These are always going to be suspect, and they're always going to be problems. The other thing that you really got to look for is battery corrosion. This board is actually pretty good. It doesn't really have much battery corrosion. It's got a little, but it's pretty manageable. So I'm using a test fixture. I'm assuming that you either have a gain. So I'm going to turn my test fixture on. And the first thing I notice is that the LED is doing nothing. That is, I got nothing. I mean, absolutely nothing. It's doing zero. So what I'm going to do first is I'm going to replace this LED. Yes, they do go bad. And also I'm going to look at the transistor right next to it. That's this guy right here, this Q2. If this transistor is bad, this LED will not flash and will not work at all. So a lot of times this transistor gets juked out by battery corrosion. So maybe you want to replace both, but I'm going to start with just replacing the LED first. Replace the LED, and we're going to apply power now and see what happens. And the LED is now locked on. But that's good. At least the LED lights up. That implies that the transistor next to it is probably okay. Not necessarily, but at least we're in a step of the right direction. We can see that the board is doing something, or in this case, nothing. So now what do we do? Well, when this is locked on, there's a couple things that we need to think about first, and that is if the core chips on this board are good. The core chips would be this one here, which is U9. That's the 6800 processor. The U10, which is a PIA or a 6821. The two ROM chips, which are right here, U2 and U6, and to a lesser extent, U11, another PIA, U6, U7 and 8, 8 being the 5101 RAM, and U7 being the 6810 RAM. So really, to get the board running, all we need are the ROM chips, this guy and this guy, and the rest of them we can kind of run without. But what I've done, or what I'm about to do, is I'm going to take these chips out and I am going to move them to a working board one at a time. So I'm just going to start removing these guys and move them to a board and test the chips in a working board. You can see that this socket's going to need to be replaced. Again, it's one of those solid frame sockets. And I always look at the pins on the chips too, and you can see that I've marked this one with a little arrow because that pin is actually broken. Look at that. The pin is broken on the chip, so it's obviously not going to run. This is the processor, the 6800. So I can either try and tag a new leg on that or just replace the entire chip. So why don't I do that and then come back. So what I've done is I actually soldered some old resistor leads onto the corner of that pin to try and save the chip. Because these 6800 processors, they're not, they haven't made them in a few years. So I don't want to throw out the chip if it just has one broken leg and I can repair it. Will that be our answer or not? I don't know. But let's try applying power. And look, the LED is still stuck on. So knowing that, what I want to do is I want to check what's known as the reset section of this board. Power off. And the reset section is right here in the corrosion zone. And it basically consists more or less of these two transistors right here. And if either one of these are bad, and they do often go bad because the battery is normally mounted right here and the corrosion likes to eat this area, it'll cause the reset line on this guy to not go high. So what happens is when you power the game on, the reset line is held low, which means 0 volts, by this little circuit, and then after 50 milliseconds or so, it allows the reset line to go high, and then this processor to start running and executing the code in U2 and U6. Now, if these are damaged, that obviously isn't going to happen, but it's easy to test. I'm using my multimeter over here, and I'm going to turn the game on, and then I'm going, with my black lead on ground, I'm going to take my red lead and go up to pin 40 here and see what I have on as far as it. And look here, I have, that's low, 0.68, that's low. So what that means is that this circuit right here is not working. One or both of these transistors are bad, or also what happens is the ground. Sometimes the grounds get eaten up, like here's a ground trace. here's a ground trace, here's a ground trace, and it goes up to the components in this section. Oh, and also here's a big ground trace. These like to get eaten up by battery corrosion. Though I don't see that as a problem here, I suspect that we just have a bad transistor. So I'll replace those two. They're like nickel items, and we'll see if we can get our reset section working. So it turned out that this transistor right here had a broken leg, and I was able to just re-tag it. And now we can see if the game starts to run. And voila, look, we are now running. And the way we know we're running is the LED right here. We saw it flicker and then flash twice. So what happens is when the LED is turned on by the hardware. When you hit the power switch, the LED goes on. But the LED does not turn off unless there is code running through the processor and the EEPROM chips here. Okay? So if the LED goes off, that means some code is being executed. So that means you're on your way to a booting game. So here, let's try this again. Flicker, then one flash, two flashes. So two flashes indicates, if we go to our chart, that this chip here is bad. I think what I'm going to do is, it's not always the chip that's bad. A lot of time it's the sockets. And again, this has the closed frame augets that I want to replace anyways, though this green one clearly isn't one of those. But what happens is all the chips, certainly in this section, get a lot of abuse from battery corrosion. So what I'm going to do is I'm going to replace this socket, and I'm also going to replace our CPU socket. And it's important to note that when you replace sockets, replace them one at a time. That is, replace a socket, boot the game, make sure it's still running. Replace another socket, boot the game. Don't do them all at once, because that way you can tell if you screwed up a trace or damaged something, it'll be directly related to the socket you just messed with. So that's why you do them one at a time. I guess I should show you, with the reset section fixed, what it looks like using our meter. So I'm going to turn it on, even though I know it's working because we've got the two flashes here. If I go up to pin 40 of the CPU chip, the 6800, and check it on my meter, it should be high. Like here, it's high. It's 5.3 volts. That's known as high. Equivalent to kind of like checking TP5 down here, which is 5 volts also. So that's what they mean by high. High is 5 volts, low is basically 0 volts. So remember before, when we had that damaged transistor down here, at pin 40 up here, when we were testing, we were getting like 0.68 volts. Well, now we know the reset section is working, because at pin 40, which is known as the reset on the 6800, the voltage is high. It's 5 volts. Why do you replace these closed frame augets? And simply put, is they're wore out. I have a simple test. It's called my finger test. That is, if I can take my finger and easily remove a chip like this, that means that socket's wasted. I should not be able to pull chips out with just my fingertip, grabbing the edge of the chip and pulling it out. If you can, there just isn't sufficient tension on the pins, and those sockets have to be replaced. Also, a lot of people ask, why don't I use machine pin sockets? Like this one. This was a machine pin socket. You can see how it has a different architecture than these plastic dual solder tail style. I like the dual solder tail, the new dual solder tail sockets. I do not like machine pin sockets. Not that machine pin sockets are bad, but they just don't have a good retention rate. That is, chip removal, in and out, in and out, in and out. Solder tail sockets last longer than machine pins. Machine pins wear out quick if you're pulling a chip in and out, in and out, in and out. It's okay for maybe this, but if you've got a board and you're set up where you're changing a lot of EEPROMs, I really don't recommend machine pin sockets. So here are the two kind of sockets that you can generally get. These are called machine pin. What's neat about the machine pin is that when you put them through the board, a lot of times you can solder it on the top side of the board because you've got more material and more metal up here. Where on these dual solder tail style, you really can't do that because of the way that they're designed. There's just way too much plastic, and also the way the pins protrude through the plastic, it's just not able to do that. But again, the downside of these machine pin ones is that they just wear out quickly. If you're doing a lot of chip insertions and removals, they just don't last a long time. I don't like them for that reason. So this is always the weapon of choice for me that I prefer, are the dual solder tail style sockets. And this is a nice one. You can see that it has metal on both sides of the pin. As the pin goes through, you got metal up here and down here. That's why they're called dual solder tail. To me, these are the best sockets. They're also far less expensive than the machine pin. For this work, I'm using a Hanko 808. This is really the tool of choice for this, and I'll tell you why. If you listen when I turn it on, see how it continually runs? So what it is you've got a hollow tip here with a vacuum basically connected to it. And a lot of ones that when you hit the trigger, they just go for a very short time, like you get a pulse. Like that. You don't want that. You want one where if you hold the trigger, the motor stays on. That way you can control how much sucking action something has. Now I have this socket removed. Look closely at the traces and make sure that you didn't bust any. It's really common for this to happen. Also, I like to take this. This is a fiber pencil. I get these at MCM Electronics. They have they make brass, but what you want is the fiberglass tip. And you can go through and kind of brush these. This works really well on corroded stuff too. The fiber really takes the corrosion off so that you can see the traces. You can also use a wire brush. This is a stainless steel wire brush I buy at Home Depot. You can do that too. It's a little more coarse. I usually do that on the back side of the board, but on the front side of the board I like to use my fiber pencil and just look at these. If I see any traces that are suspect, you can always buzz them out, just to make sure that, using your meter. This is kind of hard to do one-handed, but you can just kind of, with it on, make sure that stuff is getting through there. That you're getting good tone and that you haven't broken any of the pads removing the old socket, because it's easier to repair this stuff now than it is later. Once you put a socket in there, it's really tough to see things. So do all your testing now, not later. I don't know if you can see it, but on this socket, the U8 socket, right here, this trace here, look, it's cracked right at the front edge of the hole, the plated through hole that goes through. So you can see that using my meter, I buzzed it out from up here down to the hole, and there wasn't getting continuity. So anytime you see something like this is really easy to do. Even with nice desoldering tools, it's easy to do. So we've got to fix this, and we're going to use a stitch method to fix this socket. Peel back the green solder mask on the top edge of that trace, and then use my fiber pen to clean it up, and then I put a little solder on there. And then I take some wire wrap, and I put it in the hole, and then I will feed it across. Let's put it in the right hole. Put it there, and then I'll bend it so it's across there, and I'll tag solder it right there. So I have my little piece of wire wrap tagged to the top of the trace and then bent and through the hole. So now I'm ready to install my new socket, and this will ensure that the socket is connecting to that trace because of this little stitch that I did with the strip back wire wrap, as you can see here. And by the way, I buy this wire wrap. You can get this just about anywhere. Radio Shack even sells it. I have my new sockets installed. It's time to see what happens with the board. Remember, I replaced the 5101 socket. We were only getting 2 flashes before. Hopefully the replacement of the socket fixed the problem. The game was indicating by the flicker plus 2 flashes that this chip was bad. But a lot of times it's not the chip. A lot of times it's the socket. So we're going to turn it on. 1, 2, 3, 4, 5, 6, 7. So that, and then you notice the slight glow after the 7th CPU flash. So that means the board is now working. So I'm going to hook up the rest of the connectors and see if we can get the board is actually bringing us into a track mode. All right, let's give it a whirl. Let's look at the LED. Should get the flicker plus 7 flashes. 1, 2, 3, 4, 5, 6, 7. And sure enough, we've got score displays on. These are the CPU controlled lights you would normally see on the playfield. And you can see that the score displays are all showing numbers. Now we can put the game into test. If you don't have a wiring harness handy, you can go have a jumper wire hooked up to ground on my solenoid driver board or wherever ground is easily accessible, and then just touch the topmost pin, And now you can see the game is in lamp test. I do it one more time, and now we're in score display test, so you can see all my score displays are running. Do it one more time, and we'll go to solenoid test. 2, 3, 4. This is testing each one of the solenoids on the solenoid driver board on my test fixture. And we're running, I should state that we're running Stern M100 software here. That's why it's so systematic here. That's what's really nice about the Stern software. They go through and test each one of the transistors sequentially. Where Bally, it would test this one, then that one, then that one, then this one. So this is really nice. Okay, so we've got all our solenoids running. I'm going to hit it one more time. And now we're in switch test. And I happen to have a little test thing I can hook up here. A little board that I can run switches with. And we can see if we're getting switches. Like there's switch 1. There's switch 2. And switch 3. And this is a little board I bought from Alltech for testing their boards. So you can test the switch matrix using this little board if you don't happen to have a playfield handy. On this game, if I ground it one more time, we're just going to be into the audits, which are going to be wacky because we don't have a battery installed. Speaking of which, why don't we put a battery on this board? So I installed a coin style battery. You can get these coin battery holders, and this is a CR2032. And required me to drill a hole in the board, which I did, and then you have to install a blocking diode. So you see right here is the positive leg of the battery holder with my hole drilled through the board. Goes through a diode. This is just a 1N4001 diode, and back over to the bottom of this resistor over here, which is where the positive flow of the battery goes. It goes right here to the bottom of this resistor. Now I just want to double check to make sure that my battery is in fact installed correctly and that I am getting power to the RAM. First I'll check just to make sure that we have voltage here on the plus side of the battery, and we do 3.3 volts. Then it'll go through the diode, and on the other side of the diode we're going to get a voltage drop, and that happens just because that's the nature of the blocking diode. So now we're down to 3.02. Go over here to the bottom of the resistor, again 3.02, and then to pin 22, the last leg of the RAM, and again we have 3.02 volts. So that's plenty of volts for that RAM chip to keep memory alive, like high scores, audits, credits, and that type of stuff. So now we've got ourselves a fully working board with a nice installed lithium CR2032 battery that won't leak. Even though we had a working board before, there's one other thing I like to do on these Dash 17 boards, and that's convert them so they run a combination ROM right here, a single U2, which means that you don't need a U6. So that means you have one less socket you have to replace and one less reliability issue. So in order to do that, you have to get the code in the appropriate format, and you're going to be using a 2732 at the U2 position. So this is a combination ROM, and you have to do a couple jumping cuts to the board to make it work. Like for instance right here, I have to do a couple jumps and cuts, and then on the back side there's a single jump and cut. It's really easy to do this. I really highly suggest it. Again, it's one less socket you have to deal with on the board. Makes things a little easier, at least in my eye. But if you don't have an EEPROM programmer to program the new 2732, it's kind of not an option for you. So it's not something for everybody, but I find it to be the best way to run these Dash 17 boards. I have all the code for the early Ballys, the chime unit Bally games in this format in a single 2732. I have all the early Sterns, the M100 Sterns, in the same format. So it's easy for me to take a board and make it so that I can run any of these games, just by replacing a single EEPROM.